So everybody's okay with moving the thing to 5 o'clock?
Yeah.
All right, so I'll tell Trish. And at the end of the lecture, we should decide, do we prefer this room or room 5? It's a question of whether we want more boards or daylight. And I always preferred this room in the past, but we now have very good boards in room 5.
Well, the windows in room 5 are facing east. There's no sun. The sun's in the west by the time we have
That's
class.
true.
So it doesn't matter.
It's just colder in that room.
Yeah, it's colder in that room probably because
It's
of,
colder in 5?
because there's less insulation because of the windows.
All right, well, I'm happy with either way. If you want to stay here, I'm happy with this room.
Okay.
So let me remind you of 2 results that we got to at the end of last semester. These were fundamental path integral relations, and I think they're either, yes.
You mentioned something
Question,
about,
all right.
yeah.
Oh, Jesus.
It's the longer throw in this room.
Yeah. Hey, that's right, I didn't have to throw overhand.
You started saying something about Schwinger in the book, and I'm not Schwinger, the Schwartz in the book. Yeah, you weren't crazy about the book.
Yeah, well, I'm not wild about it. Because it's sloppy in spots. And so what I was, on the other hand, you all presumably have bought a copy or have somehow gotten your hands on something like a copy of the book, and so I'm leery about switching to something else. And in fact, there is one book that students seem to like, and it's the book by Z, which is Quantum Field Theory in a Nutshell. It is a much friendlier book. So if you, I mean, think about it, and if you want me to cover some sections in that book and skip some sections in Schwartz, I can do that. Another possibility is sticking closer to Weinberg's Volume 1, which is, it's a very good book. The trouble is that Weinberg goes into a lot of detail, and he's sometimes hard to follow. So there are ups and downs with everything. All right, let me remind you of the basic relations that we came upon. One is what is called Euclidean quantum field theory, and that's in which the fields have a dependence this way, and maybe I should rewrite this as Tx. So this is the time dependence of the fields, and one can even consider it to be a temperature dependence. And then the mean value in the vacuum of a time-ordered product of Euclidean fields is a ratio of path integrals, and over here you have just simply phi of x1, phi of xn, and then e to the minus integral. And what you have here is the Euclidean action density, and in effect it's also the Hamiltonian density. And so one can write it this way, d4 of x, and then we divide by a similar e to the minus integral h of phi d4 of x. So this gives us the, you see, since we have an e to the minus a positive definite form here, where we have something that, first of all, is converges more rapidly, and so we can do Monte Carlo simulations of this reasonably well, as long as one corrects typos, bugs, and so forth. What one is finding here is the mean value of the fields at in the ground state or at a given temperature. I thought I had an equation for that at a particular temperature, but what we can say is that the partition function, which is to say, this is being the trace of e to the minus beta h, the actual Hamiltonian. This thing is, apart from an overall constant, oh, of course I left out the fact that we're functionally integrating overall fields. This thing is e to the minus this same thing, where here the time integral goes up to beta. And so if we wanted to study the energy of the ground state, for example, we'd say that the energy of the ground state at inverse temperature beta, here beta is thought of as 1 over kT. And this thing is then a ratio of path integrals. Well, I should say it's, one can use this expression and this expression to derive it, but it's a little bit more complicated than I want to get into now. So let me just go on and to the second relation that we arrived at last time, which is for fields in normal time. And of course, in normal time, this is called then Minkowski quantum field theory. And I'm just trying to get the time relation straight because I'm always confused as to whether it's plus I or minus I. And I'm having trouble finding it's kind of absurd. I should have that equation written down in there. Good gracious. Well, I'll give you the final relation. So the time ordered product of ordinary fields in real time now, x1 up to xn, is, so this is the ground state of the theory, and this is an eigenstate of the field operator. And then we have phi of x1, phi of xn, e to the I action, phi prime 0, and then d phi. And this d phi means that we're integrating over everything, so it's also d phi prime and d phi double prime, which are at the endpoints there. And then we divide by everything except the fields. Whoops, and there I put the fields in. Let me just write it as d phi. I think that we can say d phi counts for everything, including the integrations over here. So we're just integrating over all fields. Okay, so these are our basic relations, and here it is. The equation was there, it's just I didn't see it. Here the idea, of course, is that phi of t and x is e to the ith phi of 0 and x e to the minus ith. So I wasn't sure whether it was I or minus I there. So we arrived at these things last time, and Schwartz also derived similar relations. So what I want to do now is apply these relations to perturbation theory. And there are various ways of doing that, and let me follow the way that I thought was clearest. So let's, and so far we've been talking about scalar fields. Let's consider a Hamiltonian that actually we can solve, namely pi squared of x plus grad phi of x squared plus m squared phi squared d cubed x. Okay, this is the Hamiltonian for a field that describes particles of mass m. It's quadratic. We can diagonalize this, solve this, and so forth. Fields then will evolve according to this Hamiltonian, so you put a 0 there, and that would be how they would evolve. The time-ordered product relation, the expression for the mean value in the vacuum of this theory of these fields then would be given by this path integral. And this is something that, this is one way of looking at it, and it's something that you know about. And these, of course, we can also solve for these fields as Schwartz did in the, I don't know, chapter 1 or 5 or something. This action up here would be S0, and this S0 of phi would be an integral of a half, and it would be phi dot squared of x minus grad phi of x squared, and minus m squared phi squared of x d for x. So that would be the S0 that would go here. Notice we're in Minkowski space, so we have this indefinite form. This is the Lorentz invariant expression. And if we want to write it in, this is a time derivative, that's what the dot means. This would be minus dA phi minus m squared phi squared d fourth x. In my notes, I use Weinberg's method, which is space squared minus time squared. So there's a constant minus sign when we go from here to the invariant notation. But if I tried to do it on the fly, I'd screw it up. So I'm just going to leave it this way. Any questions? Is anybody particularly hungry? I've got some of this stuff here. Okay. Now, when you've got a quadratic theory like this, one thing you can do is take advantage of Fourier's work, which allows us to convert derivatives into just numbers. And so what we'll do at this point is to set phi tilde of p as an integral e to the minus I px phi of x d fourth x. And notice this is d fourth x, so this is a four-dimensional Fourier transform. The inverse, of course, is e to the I px phi tilde of p d fourth p. And you have to put the two pi's somewhere, so I chose to put them there. If we now take this expression and put it in here, you can see that the derivatives will bring down factors of p, or ip, and we shouldn't be surprised to see that S0 of phi then is minus a half integral phi tilde of p absolute value squared times p squared plus m squared d fourth p over 2 pi to the fourth. So you see this Fourier representation really does transform everything into a much nicer form. All right, is there a question here? Does somebody want to ask a question or get a candy? No? No. All right. Okay. Notice here, p squared is p vector squared minus p0 squared, as I said, I was using Weinberg's metric. And something that I took advantage of in getting here is the fact that phi is a real field means that this phi tilde has a certain redundancy in it. And in particular, phi tilde of minus p is equal to phi tilde complex conjugate of p. So that's the redundancy that the complex Fourier transform acquires when it's the Fourier transform of a real function. This is sort of standard Fourier analysis. Okay, now something that that I don't think I did last year, and that if you want, I could do on the fly now. I hadn't prepared, I hadn't intended to do it, but I could, if you want, go through it. Let me show you what the answer is. The answer is, you see, if we're talking about the vacuum or the ground state of this quadratic and therefore soluble theory, then we can compute what this inner product is, 0, phi prime, or phi double prime. And in fact, it's that phi prime 0 is a constant that will be irrelevant, and then e to the minus a half and an integral, and it will be phi tilde prime of p absolute value squared. And this is actually 3 vector, square root of p squared plus m squared, and then just d cubed p over 2 pi cubed. So here we're using the same notation as there, but we only need the dependence on the idea, I guess, here is that we're talking about this field as we're imagining that this is way back in a particular time Yeah, I hadn't thought about this actually, that the time, I guess I'm thinking of this as phi at a particular time, and yeah, I guess that makes sense though. The complete sets of states of fields of phi are at a given time. And so you integrate over all fields at that time. That's a complete set of states. So in other words, when you say that the identity operator is an integral phi d phi, you're integrating over all functions of space, not of space-time, at a given time, and that will give you this. It's like when you say that 1 is the integral q cross q dq, you're thinking of this at some time. You're not thinking of integrating over q's that are functions of time. Okay. All right, well, that's, so the key part of this, we're not going to really be interested in the details here, but the key part of this is that the inner product of an eigenstate of the fields with the ground state of the free theory is some sort of a Gaussian, and that's Gaussian in the field, and that's basically what we'll use. And if you want, however, I can derive that. In fact, I have my notes on this here. The derivation comes from, it's in section 15.5 of my book, and if you want, it's parallel. It parallels the computation that gives you the harmonic oscillator relation, q prime 0 being a constant, e to the minus m omega q prime squared over 2h bar. So that's the analogous thing in one dimension, which is time, quantum mechanics, and in 4 dimensions, this is the generalization. If you want, I can go through that, but it's, or you can read it. I can put this chapter 15 on the web page. We might as well just continue to use the same old web page. Okay. So do you guys want to see this derivation now, or shall I just skip it? What do you think?
Yeah, I think I'll look at it on the webpage.
All right.
Yeah.
So let's see. I give candy for questions. I should give candy for answers. All right. Oh, well, these are my notes for the derivation of that inner product. In fact, I think you guys made a spectacular choice there because, in fact, there's an easier way of doing what I'm about to do. Okay, now there are 2 ways of going about this. I was going to show you the cheap way, but you know, I think Weinberg's way, which is the way I really plan to do it, is probably the better way. I'll show you both, though. I think it's good to show you both. So let's approximate the effect of these terms, which to some extent cancel. What is the change in the action? Well, it's clear that the change in the action is something that doesn't affect the action except at minus infinity and plus infinity, because here we're thinking of integrating over all fields that at minus infinity are phi prime, and plus infinity are phi double prime. And so we're doing that huge integration over all space and time. And so these things are only going to affect the action at those, at the beginning and end of time here. And the effect they have on the action, apart from a constant which is cancels, namely this factor here, this C cancels, obviously, so we can ignore it. We can say delta S of phi is what? Well, it's I over 2 integral square root of p squared plus n squared, and then it would be phi tilde of p and t plus phi tilde of p and minus t squared dqp over 2pi cubed. So that's representing this expression here at minus infinity, which I write as minus t, this little t being some huge number, and then this t being the same huge number, but with a plus sign. And so that's the effect of these terms. And now what Weinberg does is he approximates this in a sort of cute way. He uses an identity so this is the identity, and I think I should derive that for you, and now I see I've left my notes on that in my office, but I have another copy of it here, so I think I will show you the derivation of this, because this is I find this kind of mysterious, but let's go through the derivation and see what we think. So I'm going to start with the right-hand side there. This is equal to an integral minus infinity to 0, f of t, well, epsilon e to the epsilon t dt plus integral 0 to infinity f of t epsilon e minus epsilon t dt. Okay, so that's taking this thing and writing it as two integrals, so we don't have to deal with the damned absolute value. And now this thing is a derivative, this term here, and so we can rewrite that as minus infinity to 0 f of t d dt, which is very effective against malaria. It's too bad that it's been banned, actually. What's also effective against malaria, though, are bats. I forget what it's called, fish-tailed bats or something. Does anybody know? Free-tailed bats are remarkably effective against malaria. And some doctor in Austin about 100 years ago created a bat hotel in Austin because he was concerned about the incidence of malaria. And once he constructed the hotel and built up his population of bats, the malaria incidence went down significantly in the city of Austin, which I guess was a town back then. And it was so successful that he got the state legislature to put make it illegal to kill bats. And so basically Austin was malaria-free until, of course, the media came in with a movie about frightening people of bats, and they repealed the protection of bats. So this would have been a disaster for the city of Austin, but the city or the state built a bridge across the river. There's a river in Austin. Texas is wet as opposed to New Mexico. Anyway, there's a river, there's a bridge, various bridges across the river, and one of the bridges was constructed either on purpose or by accident in such a way that it functions as a perfect hotel for bats. So bats come up from Mexico in, I don't know, March or something, and they stay there until October, and then go back to Mexico. And so then for the warmer months, they protect the Texans from mosquitoes. Enough stories. Okay, so that's one part of this. And the next of this, you see, we put a minus sign here, and we have 0 to infinity f of t d dt e to the minus epsilon t dt. Okay, so this is that identity just rewritten slightly. And so we can now rewrite this whole thing as two integrals, namely integral minus infinity to 0, and I'm going to say d f of t e to the epsilon t. I'm sort of doing the partial integration by hand, minus e to the epsilon t df dt dt plus, maybe I'll just write the thing here, and actually it's minus integral from 0 to infinity of d f of t e to the minus epsilon t dt minus e to the epsilon t. Actually, wait a minute, minus epsilon t, right, df dt. Okay, so this is just doing the integration by parts laboriously. So in other words, this thing here is the the derivative of the whole thing minus that, and this one is that. Okay. Now, what can we do? Well, this derivative here, what does this give us? This gives us f of 0 times 1, and then the other term, well, the other term is surely 0, because it's e to the minus infinity. And so what this gives us then is f of 0 minus the integral minus infinity to 0 e to the epsilon t f dot of t dt. And then this term is, well, we've got this. And so this gives us this evaluated infinity, which is 0, and then minus its value of 0. And so that gives us plus f of 0, and then plus integral 0 to infinity e to the minus epsilon t f dot of t dt. Okay. Now, we're going to let now epsilon go to 0 here. And notice the difference. Here, we've kept epsilon, and when t is in the boundary terms, the epsilon is really effective because t is only plus infinity or minus infinity, or 0, in which case it has no effect. On the other hand, here, this epsilon is is being applied to t's that are finite. They're t's that are 0, 1/2, minus 10, and so forth. And in here also, the epsilon is applied to numbers that are finite, and so we can take the limit epsilon going to 0 here. When we do that, effectively what we're doing is just replacing this by 1. So this is the sort of lobotomy limit. And now we see what this gives us. This is very simple. This gives us f of 0 with a plus sign, which cancels, and so this gives us f of minus infinity, and then this one gives us plus f of infinity, and then minus f of 0, which cancels that. So what we get is this final relation, namely that for suitably regular functions, f at infinity plus f of minus infinity is the limit, epsilon going to 0 through positive values. F of t minus infinity plus infinity integral e to the minus epsilon absolute value of e dt. Okay, that's what we've got here. We've got something like that here because we've got an integral here which, well, no, this is, sorry, we'll leave that the way it is. Whereas here, what we've got here is we've got something at plus infinity and something at minus infinity. And so we can rewrite that, get the rest of my notes. We can rewrite that as lim epsilon goes to 0 plus of I epsilon over 2 integral square root of p squared plus m squared integral minus infinity to plus infinity by tilde of p and t squared e to the minus epsilon absolute value of t dt dqp over 2 pi q. So we've rewritten these boundary terms, which of course come from these terms. We've rewritten them in this way. Now we're going to approximate this. It's going to turn into almost nothing at all. And we're going to say, well, to first order, we've got an epsilon here. And so we can forget this epsilon, because that's a factor of order epsilon squared. In other words, yeah, I know, it bothers me a little too, but let's just do it. So that thing then is this limit again of I epsilon over 2, square root then of p squared plus m squared by tilde of p squared d4 p over 2 pi cubed. What we've got here is this thing integrated dt. This is a Fourier transform effectively, and it takes us to, well, effectively p0 times the 0 component is effectively 0 there. Anyway, that's our expression, and we're really, and so the total action then is now S0 of phi and epsilon is S0 of phi plus delta S0 of phi. And so this is minus a half integral phi tilde of p squared. And now what we have is p squared plus n squared. That's what we had before. And then we have minus I epsilon square root of p squared plus n squared d fourth p over 2 pi to the 4. Okay. Now at this point, we're taking the limit epsilon to 0, so a factor here doesn't matter. So we blow it away. And so what we have then is our new action is S0 of phi and epsilon then is minus a half integral phi tilde of p squared, p squared plus n squared minus I epsilon d fourth p over 2 pi through 4. All right, so you notice what happened is this thing, which of course will turn out to be the denominator of the Feynman propagator, it acquires the I epsilon. And this is the correct sign for Weinberg's metric, or Schwarz's metric. It's p flips and the so forth, and might be a different sign. Now, let me give you the quick and dirty way in which this occurs. The idea, remember that when we derived this, what we really had was an e to the minus I th there, and we had an e to the minus I t h there. So we had really e to the minus 2I th, where t is essentially infinity, and that's taking us from minus infinity to plus infinity. This is time evolution operator. And so what we want to do, of course, is we want to be projecting out the ground state. Well, the way to project out the ground state is to replace that. In other words, instead of having e to the minus 2I th, which is a h or h0, is we put in here, we call this h minus I epsilon. And now what we've got is minus I squared is minus 1, and so we have minus infinity epsilon. And actually, now that I think about it, that is a little too quick and a little too dirty. We need that epsilon multiplying the h. So in fact, it has to be this way. Now, now we've got e to the minus epsilon h. That's projecting things out. And so this would give us, this means that the effect, the whole action has to be, this is sort of equivalent to having, instead of e to the I L dt, we have here 1 plus I epsilon dt. Okay? And the addition then of an I epsilon to the action is I mean, the action is here, and then something involving p squared, and something involving p squared, as long as it's positive, we can drop as an epsilon. Okay, that was a lot of hand waving. As I said, that's the quick and dirty way of doing it. The Weinberg way is the gold standard. Okay, so now what we've got is that we've got the time-ordered product of the fields, and these are real time. Is then this ratio of path integrals phi x1, phi xn, e to the I, and s0 phi epsilon d phi, and then we're dividing by the e to the I, s0 phi epsilon. So that's what we've got at this stage. And now we're going to introduce something that's basically a mathematical trick, but it's so useful that it's become almost a fetish in theoretical physics. If you don't have this C number current, and if it doesn't occur in exactly the way I'm about to write it down, people will look at you strangely. Anyway, this is the definition. Ground state, time-ordered product, e to the I integral j of x, phi of x, d4 x. Okay. So that's the z. Now we can see what that is. Namely, that's just, if we expand this exponential, it's just lots of products of fields times j is not quantized. J is just a function of space-time that we're going to use as a trick. And so this thing takes the form over here. So let me write sort of as a long integral sign. It would be integral e to the I. And then this would be, first of all, S0 of phi and epsilon. And then it would be plus I integral J0 of x, phi of x, d4 x, and then that would, d phi, and that would be divided by e to the I S0 phi of epsilon d phi. So in other words, an application of this formula to this expression gives us, I forget the name of this thing. What do we call it? No, I didn't name it. I'm not big on names. I forget names. You know what it's not the partition function. It's what? It's let's just call it Z. So Z is then this ratio of path integrals. Okay. Now it's very what?
Well, I think it is the partition function, right?
It's what?
The partition function.
I thought the partition function was trace of e to the minus beta h.
You mean, okay, the quantum wave.
Well, it's like the partition function, at least in that both are often written as Z. All right, anyway. Obviously, Z, if you set j equal to 0, you just got the mean value of 1 in a normalized state. That's 1. So Z0 of 0 is 1. Okay, so we understand that. On the other hand, we can compute, we can rewrite, we can absorb this linear term, J0 phi, into S in a rather cute way. This is just this old completing the square business, which we all learned in high school. And of course, in high school we had no idea how so we're going to write S0 of phi, epsilon, and j as S0 of phi and epsilon plus integral j of x, phi of x, equal x. And remember, j is a function, simply. And it has a Fourier transform that's also a function, j of p, e to the minus I, px, j of x equals x. And let me see if I'm still putting the two pi's in the right place. Yeah, the p is just d4th x, and going the other way we get 4 factors of 2. Okay, so what is this modified action? Well, it's equal to minus a half integral phi tilde of p squared plus m squared minus I epsilon minus j tilde star of p phi tilde p minus phi star tilde of p j tilde of p. Tilde just means Fourier transform. And all of that p4 t over 2 pi and 4. Okay, so the action with all these, the action with the epsilon and the classical current gives us this. This step, though, from there to there was, I call, well, I thought of it as a problem, but it's hardly a problem. I mean, it's just, you just write j of x in terms of its Fourier transform. You write phi in terms of its Fourier transform. And they wound up, what actually happens is that this is phi tilde of p, j tilde of minus p. But j tilde minus p is j tilde star of p. And the same thing happens over here. And the reason you get minus p is that if you have something that is an integral, j of x is then j tilde of p e to the, oh Christ, it's backwards, e to the I px, and then you have phi of x, so that's phi tilde of, let us say, q, e to the I qx, and we're doing a d4th x, and we've got 2 pi to the 8th because we had to go backwards to get this, okay? So, once again, Dirac comes to the rescue and gives us 2 pi to the 4th, but q is minus p. And so this is integral j tilde of p, y tilde minus p, over 2 pi to the 4th. And there's no more. Well, this, oh, I forgot, this d4th p, d4th q, and the delta function means you get rid of one of them, so you have d4th p. So this is what you have left. And you can, because of the 1/2, you can rewrite that as 2 terms like this. All right, any questions before I go to the next step? I just wanted to come up here to get a sip of tea. All right, the next step is a change of variables. And so we're going to set psi tilde of p equal to phi tilde of p minus j tilde of p divided by p squared plus m squared minus I epsilon. Okay, and so the next step, what we're going to do is we're going to say, well, phi tilde is psi tilde plus all this. And so we write that, we make that substitution in here. And then what happens is we get a rather nice expression. This thing is crafted so that when you make this substitution and put it in here, these linear terms cancel. And we just get something like this with a psi, and then something involving a j squared. Okay. Now, if you want, I can go through the details of that. No? Okay. All right. Okay, so this S0 then of phi, epsilon, and j is S0 of psi and epsilon. In other words, it's exactly this expression, but with psi tilde. And then there's the quadratic term that survives, and it's an integral j tilde star of p, j tilde of p, divided by p squared plus m squared minus I epsilon, d4 of p minus 4. Okay. So that's what basically the action turns into when we're representing this time-ordered product of this exponential or linear expression in the field. So, but now the thing is kind of interesting, because you see this Z0 of J now. What is it? Well, it's an integral e to the I S0 of psi and epsilon plus a half integral j tilde star j tilde over this p squared plus m squared minus I epsilon before p 2 pi to the 4th. And this thing is still d phi, and it's divided by integral e to the I. And down here, all we have is this. So this is e to the I S0 of phi and epsilon d phi. Now, the cool thing is the following, that when you change variables like this, the Jacobian is 1. Okay, so it's a derivative of this with respect to that, and this thing doesn't make any difference. Okay. So in other words, we can write this thing up here as d psi. But now the d psi S0 of psi and epsilon, psi is a dummy variable. So since it's a dummy variable, it doesn't care what we call it. And we can call it phi. So I'm going to call it phi. Now something really remarkable happens. The path integrals cancel. And so the only thing that's left is this exponential. So we've actually computed Z0 of J. Namely, it's e to the I over 2, an integral j tilde of p, absolute value squared over p squared plus m squared minus I epsilon d4 of p 2 pi to the 4. So because this theory is soluble, we can actually compute things. And so this is the mean value of that exponential linear in the field with a psi, and this is functional. All right. Now this is a very useful mathematical thing. In particular, if we go back to position space, my wife never calls unless I'm teaching. Yes.
Did you read my message?
What?
I read your message. Did you read it?
No, I didn't. I've been teaching.
Oh, you have started.
I'm teaching now, actually.
Oh my God, bye.
Yeah, I'm done in about 10 minutes.
Okay, bye.
Fine. All right. Okay. Well, I think rather than just skipping this derivation, I think I should do it because A, it's simple, and B, it's important. All right, so what we're going to do now is go back to position space. So what we get is then e to the I over 2 integral, and this will be j of x to the I px, j of x prime e to the minus I p x prime. Why minus? Because we're complex conjugating the other one. Will be the d4th p 2 pi to the 4th from here, and we'll be integrating d4th x prime, and of course I forgot to divide by p squared plus m squared minus I epsilon. Okay, well, what we have then is e to the I over 2 integral j of x delta of x minus x prime j of x prime d4 of x prime. In other words, where delta is what's left here. In other words, delta is Feynman's propagator, namely delta of x minus x prime is this integral e to the I p x minus x prime over p squared plus m squared minus I epsilon d4 p over 2 pi to 4. So in other words, this thing is e to the I over 2 j of x prime, integrating over space and time, both x and x prime, and in between the Feynman propagator. Okay. So that's really a very nice result, and what we can do now, what one does at this point is one writes z0 of j equal to this, and now one functionally differentiates with respect to j of x or j of x prime. And on the right-hand side, that just pulls down Feynman propagators and j's. On the left-hand side, on the other hand, this thing is still equal to 0 time ordered product e to the I integral j of x phi of x d4 of x. So on the left-hand side, the functional differentiation with respect to j pull down fields. On the other side, they just pull down numbers, these constants, these currents. And in fact, We then get rid of the currents by evaluating these functional derivatives at j equals 0. So on the right-hand side, all we're left with is some thing involving the Feynman propagator. And over here, after we've functionally differentiated and set j equals 0, all we have are fields. So this is a recipe for expressing the mean value in the ground state, time-ordered products of fields in terms of Feynman propagators, integrals of Feynman propagators. Now, I think I should review for you what these functional derivatives are, because we don't get taught about that when we're in school. I know when I was a graduate student, because I skipped all these courses that I should have taken, who knows, it may have been that functional differentiation was in one of these courses. I don't know. I don't think so, though. I think all that was in those courses were Bessel functions and Chebyshev polynomials and so forth. All right. So let me show you how this goes. And this is actually, it's funny, it's one of the cases where the mathematicians, instead of making things difficult, have actually really clarified things. So this is in chapter 15 of the book. I'll put it on the web page. So let's say we have some functional g. And now I'm going to define a functional derivative in this way. G here is a functional of two functions. So it's something that maps a function f and a function h into a number. The number is g of f and h. Okay, and then delta will be the functional derivative part. So this I'm going to define as d d epsilon of g of f plus epsilon h. I don't know, I think maybe this was overkill, but anyway, at epsilon equal to 0. So that's the idea of the functional derivative. Now, all right, let's take as an example. Suppose g sub n of f. Oh, we don't have a hell of a lot of time left. Suppose this was just equal to dx fn of x. So that's a functional. And so what is, so we start with this functional. What is this functional derivative? Well, we add in an h. And we say this is d by the epsilon of g of f plus epsilon h, of course at epsilon equal to 0. And so this is d by the epsilon integral f plus epsilon h to the n of x dx, again epsilon equal to 0. Now if you expand this thing, first term is f to the n. Doesn't involve epsilon, so the derivative is 0. The second term is nfh. It's f epsilon. Let me get this straight. It's f to the n minus 1 times n times epsilon times h. The higher terms have higher powers of epsilon. So when you take the derivatives at epsilon equals 0, they go away. Okay. So the only thing that's left here is integral dx and f to the n minus 1 of x, h of x. Okay. So this is the answer in this general context of a general functional derivative. But now, physicists don't normally use this generalized functional derivative. Instead, they consider only effectively a Dirac delta function for h. So this h, instead, is going to be, here's the physics notation. So the derivative of the function with respect to f of y, this is physics notation. Put it in math notation, it is this variation g f, but now h is deltas of y, where deltas of y, of course, is the function delta of x minus y. So now, what we have is, in physics notation, the derivative of the functional derivative is then this integral n, now h is delta of x minus y, and that just gives us f of y to the n minus 1 times n. All right, so this is a way of defining and making precise these functional derivatives. So we've run out of time, but next time I'll just use this clear definition and apply it to this functional, and we'll see how this thing works. I know I was very much relieved when I came upon this material on functional derivatives. You might say, where did he get it? Got it off the web. All right. Okay, I guess we can end it. Any questions?